So let me continue from last time. So last time we have seen two things. One is expanding balance separator, right? And this is just expanding balance separator is a set of edges, F, such that F is expanding in G, and also it's a balance separator. That is, when you remove F, then each part has, like each component has less than n/2 nodes. Okay, so we see this. Good. And next is that we also see the definition of where is it? Okay, Separator-Expanding hierarchy. Okay. So good. So this is just a hierarchy, right? It's a hierarchy H such that for every cluster H in the hierarchy, its separator is expanding in the cluster. For example, if you look at the root hierarchy, at the root cluster, which is the whole graph, the separator, which is like the red edges that separate the whole graph, is expanding in G. And if you look at like the Schroeder cluster of the root, which is like H1, H2, H3, well then if you look at this cluster, H1, the separator of H1 is phi expanding in H1, and so on. So, okay. And another way to view this is to view like, so basically, another way to define the separator expanding hierarchy is a partition of edges. Okay? So you partition edges into levels. Level E0 up to EL. And you think of EL, or for each I, EI is like a separator at level I. Basically, that's how you think about it. So EL is a separator at the top level, so it separates the top level, and it's expanding in G. And EL-1 is a separator at level L-1, so it kind of separate. And what it has is expanding in G minus EL, which means that in the component after removing EL, EL-1 in each component is expanding in each of these components. We're good with this definition, right? Okay. Good. So now, I claim that for any graph, you can build this 1/4 separator expanding hierarchy, where the number of levels is just log n. Okay, and the construction is really simple, given that we know how to build the expanding balance separator. Okay, so the algorithm is just first compute the expanding balance separator. Okay. So that you think of that as like the separator at the top level, and say that that's EL, and then you recurse. Okay. Recurse on each component. So the algorithm would be like you start with the graph, you compute EL, it separates the graph into pieces, each of which is less than half, and this is expanding. And then for each component, just compute the separator in each component and call that EL-1, and so on. So do you see that this must give you a separator-expanding hierarchy? Right? It's just really like by definition, for each component, for each cluster, you get some separator that is expanding. And then you recurse on each of these components. This thing, you get some component, like you recurse in the next level, and you get like EL-2, and so on. So, and this must be 1/4 expanding because each of these EL is 1/4 expanding. Why? Do you see why the number of level is just log n? Why is that? Anyone? Yeah.
That'd be because kind of when our separator breaks it, the graph or the nodes into the pieces, each kind of piece has at most n/2 nodes.
Right. Yeah.
So we keep kind of breaking it. That's where the log factor comes from.
Exactly. Yeah. When you recurse, the number of nodes get halved. You can halve the number of nodes at most log n times. That's why the recursion depth is log n. Okay. Okay. So really simple to obtain, and actually this is the state of the art. It already improved what's kind of known some years ago. Okay. So this is what we have. And for any graph, you can build like 1/4 separator expanding hierarchy. I just call SE hierarchy from now, with log n levels. Okay. So this is how you think about it. Given any graph, you can find like there's gonna be like the separator EL that is expanding in G, right? And in each of these components, this is a component that consists of edges of level less than L. This contains edges of level less than L. In each of these components, there's going to be some separator of level L-1, and so on. Okay. So I hope this picture makes sense to you. Does it? Yeah.
Also, what would be the runtime to construct such a hierarchy?
Good. So if you can compute the expanding balance separator in nonlinear time, that would be nonlinear. Right now, the algorithm that I described to you, like it's just ask if there is a sparse cut or not. That is an NP-hard problem again.
So it will be exponential.
It's exponential, but we'll see how to do this in nonlinear time in 2 weeks or something, in a week or two. Yeah. When you pay, instead of constant here, you pay some log factor. All right. Okay. So now we know what is the SE hierarchy, right? And now we come back to our goal. Okay? And let me recall the goal. The problem that we want to solve is the connectivity oracle. Okay. It's this problem, right? You pre-process the graph, and then given any kind of one batch of deletion D, then you can compute a representation of the connected component in the graph after deleting D. That's what we want to do. Okay. So that given this representation, you can query any ST and answer it in like log n time or something. Okay. So we see how to solve this on Expander. So now, given that we know the hierarchy let's see how to solve general graph. Okay. All right. Okay. Go to general graph. Okay. So the strategy that we're going to use is the bottom-up strategy. We will try to kind of, you have a whole graph, you have a hierarchy. Given a batch update D, you try to deal with like the bottommost hierarchy first, and then go up next level. Yeah.
So is the cluster like expander? Is that basically analogous to like the repeated expander decomposition sort of?
No. So you see, here you really have hierarchical structure, as in like, just like the bottommost level is like the top level is like the whole thing. The next level is just like the refinement of the top level, and so on. So this have a hierarchy structure, but if you look back to when we talk about repeated expanded decomposition, you have like log-n graph, but this graph they don't respect the partition to each other. Make sense?
Yeah.
Yeah. So good. Okay. So come back to this. The strategy is bottom up. Okay. And imagine that you have done something from level 0 up to level I minus 1. And now I'm just going to tell you what we want to do at level I. Okay. So at level I, we have a level I cluster. Okay. I denote it by h at most I. Why do I use at most I? Because at level I, you have edges up from level 0 up to level I, right? Each cluster at level I has edges from 0 up to I. Okay. The edges from level above is not in this cluster. Okay. In particular, if you look at this h, then there's going to be like this separator that is expanding, and each of this has like each of these component contains edge of level less than I. Okay. So look at this cluster, and now consider the deleted edge inside H. Okay. And we need to do something about H. Okay. So what I'm going to do is just assume that I know the. Okay, let's look at this picture. Yeah. This is like deleted edge in H. There are like the orange one here and the red one here. These are the deleted edge. Okay. I use the orange one to denote the deleted edge at level less than I. So it's kind of inside the children of H. And the I is like the deleted edge at level I. Okay, so now because our strategy is to do things bottom up, we're just gonna now assume that we now know the connected component of children clusters of H. So like you have some deletion in this child. We assume that we know the connected component of this graph after deleting. Okay. For example, like this. You kind of, if things really get separated, you know that this component that was connected now got separated into two parts, like this. Okay. So the lower level child report, like give you like this component for you. Okay. All right. So now, but what we want to do is like, we want to update the connected component of H. Okay. So we are done for lower level. We want it to be done on this level. Okay. For example, we kind of want to detect this structure, for example. You know the lower level gives this structure to you, and you want to detect this structure. That, okay, for level I, you get the new component. H actually gets separated into this component and the rest. So that's the goal. Okay. And what we want to do is like, we want to do this in time proportion to the number of deletion in H. Okay. That's the goal. And if we can do this, then we are done. Because it means that if we just do things bottom up, then after updating the top level cluster, G, the whole graph, then we would know the connected component of the whole graph. Make sense? And the total update time is going to be something like D times the number of levels. Right? Because the total time on level 0, you just spend time on each cluster. At level 0, the total time is going to be D, because you spend time proportion to the number of deletion on each cluster, and then next you spend another D time on the next level, another D time on the next level. So there are log n levels, so the total time is still something like D log n. Okay. So now let's see how do we deal with like how to solve this task. That's now our goal. Okay, so here is the algorithm. And if you remember, the algorithm from last time is going to be quite similar, but like it's quite subtle actually. So what we're going to do is we're going to initialize a passive region. Okay. And the passive region is what? It's going to be components of all children clusters. Okay. So, oh, wait 1 second. I want to have 1 sec. Okay, doesn't matter. So do you recall what in the algorithm for expander, what is the initialize, like what is the initial passive region for it? Yeah.
Just the node itself?
Yeah, it's like a singleton, okay? It's just because for expander, we kind of know from the beginning that each node is a kind of connected region, like it's kind of trivial connected region for each node. But now we are at level I, and each of these components from like, what I mean is that look at the components that's from the children cluster. Each component reported by the children cluster are connected. So we just treat that as a connected region that is kind of initialized for us. Okay. And we're gonna have defined an active region in a similar way. And we define it like this. It's active if it is incident to a lot of deleted edge, but in some subtle sense. Okay? So you count the number of edges at level I. This is like a degree I of u. What's degree I of u? Is the total number of, degree EI of u. So you kind of count the the number of edges at level I incident to you. Okay. This is degree I of u, and you ask if degree I of u is small compared to deletion incident to you. But this deletion, I counted for edges up to level I, not just at level I, from 0 to I. Okay. So this del at most IU, you count the number of deleted edge up to level I. Okay. So this just said that if like the volume at level I of U is small compared to deletion up to level I at U. If that is the case, then you said it is active. Intuition is still the same. If you are incident to a lot of deletion, you should be active. But this is a subtle point. Okay.
So degree only counts like the blue edges. Deletion also counts like the deleted edge within the component. Is that?
Say again, sorry.
So like the degree only counts the blue edges over there.
Yeah, degree only count the blue thing, exactly.
And the deletion can be like within the component.
Exactly. For the deletion, you count the thing within the component here too. Yeah. Good. Okay. And also, similar to what we have before, we're gonna say that the region is active only if you could still have a chance to grow the region. That is, it should have some unexplored neighbor in this graph, in H minus D. If there is no way to explore further, then it should be isolated. You cannot go further. Okay. So it's active if you can still do something about it. Yeah. Okay. And the algorithm is just like this. Like before, previously we just look at the active region and keep growing the region until it's passive or isolated. We do the same here. Look at the active region. If it's active, then there is like this region U would have some unexplored neighbor of U. Look at the region that contains this neighbor, UV, then merge the region together. Okay. Once you merge, you just check if it should be still active or not. So if now the volume is big compared to the deletion, where you have I and at most I here again, right? If the volume is big, then it becomes passive. And if it has no neighbor left to explore further, then it's isolated. Okay. And the claim is like before. For each isolated region, you know that it's one connected component for sure. And everything that is passive, we're going to claim that they actually are in the same connected component. Okay. So you see it's the same structure like previously, but there's some subtle point here. Yeah. Okay. So let me give you some animation, right? So if you look at H and you have some deletion, the deletion from level below, the orange one, and the deletion at level I, at our level, okay? Then the initial region is that like we're gonna look at the component from level below, and each of these components will be initial regions. Okay. So in the beginning, maybe like this one is passive, And this one, maybe it is incident to a lot of, deleted edge from level below or level I, then this thing become active. Okay. Makes sense? Like you can see now that it makes sense to count deletion from level below too, because like the deletion from level below might like separate things. So you better explore from the component if it is incident to a lot of deletion from the level below. Okay. Yeah.
But we're still like treating those two components as like separate regions.
Yeah. Initially, these things are separate region. Yeah. Okay, good. So now, let's say that I just gonna start exploring from this active region. Okay. So I find one neighbor here. Like this is my neighbor, and this is V. This is region of V. So I merge it, and maybe it's still active. So I go further, and then I merge. Okay. And then there is still another neighbor here. Then I go further. Okay. And merge. And now, once I look at this region, all of my incident edges that go out is already deleted. So there is no unexplored neighbor that I can go further. So it becomes isolated. Okay. At this point, I'm not done yet because there's something active here. Right? So let's explore from this guy. So maybe I merge to this guy, and I go further. And now, like the blue edges is big enough compared to the orange or red edges incident to it. So that's when I say, okay, blue is big enough. The number of blue edges is just big enough. So it's now passive. Okay. Question? Yeah.
So the algorithm is like very similar to the previous lecture algorithm.
It's very similar, super similar, except that it's kind of, the only difference is really just like, what is the threshold here?
Yeah.
Here you kind of count the number of blue edges compared with red and orange edges.
Yeah. But the important observation, like the most important part is that the union of all the green parts has to be one component.
Yeah, right, exactly. So the claim is just there are still many passive regions, but we claim that all the passive regions are actually in the same component. Okay, so let's prove it. And the proof will kind of follow the same template like before. Okay, so we're gonna prove that all passive regions actually are in the same component in H minus D. Suppose not again. Suppose that the passive region here are not connected somehow. Like there are some can be separated somehow. Okay. So then there exists some set B such that B is a component. Okay. And B is a union of passive region. Like this. And we know again that B cannot cross any passive region, right? B cannot be like cross any passive region because each of the passive region, we know that it is connected. So B cannot look like this. Okay. So suppose that you have the B like this. Okay. Component is like union of green region, and yeah, it's disconnected from the rest. Okay. So now what do we know? We know that the number of boundary out of B, edges that go out of B, need to be big, and actually this is edges up to level I. Okay. This thing need to be big compared to number of blue edges in B. Okay. Why is this?
We know that each region has to be an expander in the edges.
Yeah. It's not just each region. You kind of know that the blue edges is expanding.
So it would be the separator that's expanding.
Each cluster, I guess.
No.
Right.
Not really. Like we know that in this H at most I, right? EI is expanding in H. Okay. So it means that if you look at any cut, then you know that the number of edges in H at most I that crosses the cut need to be big compared to EI. Okay. Does it make sense? Like, this is the number of edges crossing the cut in H, and it's going to be of level at most I at most because H only contains edges up to I level, from 0 to I. The number of edges, the cut edges of H crossing any cut B need to be big compared to the blue edges compared to blue edges. Okay. So EI is phi expanding. Okay. Yeah, this is just because EI is phi expanding. All right. So we know that like you cannot expect that there are a lot of edges crossing BI. Okay. Crossing B. But at the same time, like the number of deletion incident to B will be small.
That's because B is passive?
Yeah, exactly. B is a union of passive region. So this need to be small. So how small? Deleted at most I of B is at most phi degree I of B at over 2. Okay. So yeah, because B is a union of passive component region. Yeah. Okay. So once we have these two, we know something. That is, okay, there are a lot of cut edges crossing, but the edges that is deleted incident to B is small. Okay. So it means that there must exist some cut edge crossing B that is not deleted. So there must exist something like some edge crossing that is not deleted. Okay. So it means that B is not a component. Yeah. Okay. Question about this? Yeah.
So we basically combined the two inequalities and we got like the number of edges crossing the cut is greater than the number we deleted.
Yeah, exactly. Yeah. Combining these two, we get this thing. Yeah. Okay. Good. So we are done with the correctness. And the update time, well, suppose that, let me denote D prime by the number of deletion in H, right? I claim that the update time is proportional to D prime. And the reason is this. Okay. So I claim that the total level I volume, so the total degree I that we explore is going to be something like 4D over phi, 4D prime over phi. And the reason is that, well, like we only explore from the active region, but active region is such that the degree I is small compared to deletion. Okay. And the total number of deletion is at most 2D prime. Okay. So, okay. So this is true, but now, like, the data structure part is actually a bit more complicated, right? Because not too much complicated, but if you look at the algorithm, what I want to say is that, like, we kind of spend time. The time that we spend is just kind of proportion to the blue edges. Like the time that we spend is the time that we spend. Like, okay, what I mean is that the algorithm will spend time only on blue edges, not the region inside, right? And the number of blue edges that we explore in total will be small compared to the red edges, the red or orange one. And even if some region, the green one is so big, we're gonna not spend time there at all. But that we can do because we think of this region as maybe like you contract this to one node, or you use union file data structure to think of it as one node. Okay. So like the big region, the green thing, we don't really spend time inside at all. We really just spend time on the blue edges that connect the green region, connect the initialized region together. So that's why, like, it's okay to just bound the total level I volume that I explore. This is level I volume is like the blue thing, the blue edges. Yeah.
The D prime or 4D prime over 5, does it come from our original condition in the DFS? Or?
Yeah, exactly. Like we only explore further from active region, and active region is because it's the one such that the number of blue edges is small compared to deletion, and number of deletion in total is at most 2D prime. So it means that the sum of the blue edges that we explore, is at most, yeah.
4D over.
Yeah. Right. Okay. But yeah, this is true. This is just combinatorial claim, but you now need some data structure for merging region, and you think about it how to do it formally. Yeah. Okay. So now we are done. We get this.
Sorry, can we go back to the previous slide? The slide before this. Yeah, so like where do we use the fact that B is not the entire, like the union of all the passive regions?
Oh, here. We need it here. Like the reason that the number of deletion is small compared to blue edges is because each of these are passive. Right? Because if this is passive, if U is passive, then you know that from the definition that degree I of U is big compared to 2/5 degree delete at most I of U.
Yeah, but does the same argument still work if I take like B to be like the union of all the passive regions? Like it's still a union of passive regions.
Well, but then we're done.
B
No, but if I do the same argument there, would it still like?
if B is the whole thing,
Yeah.
then we don't prove anything because we want to prove that we suppose that the passive region are not connected. And I just said that like a B is like a component that shows that passive region are not connected.
Where do we use this fact? Do we use it somewhere?
Which fact?
Like use the fact that it's just a component.
The fact that which fact again? I don't know what you mean.
The fact that there's some, like P is not the entire union of all the passive.
This is the whole point of this statement. Like the point is to prove that the passive region actually like form the connected component, and we suppose that it's not the case. So if it's not we prove by contradiction that this is not the case. So it means that there is some way to that the passive region are not connected. It means that there must exist some set where B is not the whole passive region. Okay? All right. So we are done. We now get the connectivity oracle such that you just spend basically linear time on the number of deletion. Okay? Like D times polylog. And this works in general graph. So I hope you see that like this is the power of the hierarchy, that you have ideas on expanders, and if you know it, how to solve an expander, you kind of generalize nicely to the whole, to any graph. Okay. So now you kind of know two ways to generalize idea from expanders. One is repeated expanded decomposition, right? The one when we when we solve H specifier. This is just another way. Yeah. Okay. So this is what we have so far. Okay. We learned that the graph, like expansion kind of means that the graph is robust under deletion, and we learned how to solve this one. And what's important that I want to tell you is really this thing, SE hierarchy. Yeah. And we know how to construct it in the top-down way. Once you can compute expanding balance separator, just do it and recurse. You can construct this hierarchy in top-down way, in easy way. Okay. Good.